Hello there, my name is Robert Thorson, and I'll be talking about automatic test pattern generators. What is an automatic test pattern generator, or ATPG for short? An ATPG is a program usually consisted of a code run through a computer to test a digital circuit for faults along the design, manufacturing, and post-manufacturing process. These testings is important to ensure the reliability of the components being produced. Given the complexity of components today, newer and faster methods are being continuously developed to ensure reliability and quality of the digital circuits. ATPG basics. Defects can arise during manufacturing, which allows the ATPG to detect faults in the process of manufacturing or after manufacturing. The ATPG provides a pattern to the input of the device called a test vector, which is an algorithm that performs two types of signals: fault activation and fault propagation. During the testing phases, the digital circuit goes through a variety of tests to determine whether the pattern applied on the input terminals match what is expected on the output terminals. If it matches, there is no fault. If it doesn't match, there could be a fault and further testing occurs. ATPG basics continued. ATPG testing isn't foolproof for a single battery of tests. Testing takes time, and time is inversely proportional to the accuracy of the test being performed. There are a variety of faults that can occur: bridging faults, stuck-at faults, transistor faults, open faults, and delay faults. There are other faults to consider, but we will be covering just these 5 in this topic. Fault modeling. When it comes to bridging faults, there are 2 or more signals that are crossed, bridged together where they shouldn't be. This would result in errors occurring on the output terminals where one or more outputs are showing the exact same output where it shouldn't be. Stuck-at faults. This is where the value is stuck at a 0, a 1, or an X, i.e. don't care. This fault is very typical compared with other faults, but also very typical with delay faults as far as frequency of occurrence. Transistor faults. The fault modeling is used for CMOS gates and circuits to ascertain stuck, open, or short conditions. When it comes to CMOS transistors, stuck-at faults testing is not conclusive when it comes to looking for stuck on or stuck open short faults. And what I mean by stuck on, stuck at 1 or stuck at 0 faults, because of the inherent nature of CMOS transistors to begin with. With open faults, there is a broken wire or pin preventing the input from reaching the output mechanically. This is probably the easiest fault to understand as far as how it works, much like a broken wire. Physically, the signal is not connected to the chip in one way or another, either on the input or the output. And a delay fault. The delay fault, the circuit actually functions, but with an inherent delay. This delay can be in a variety of configurations, whether in nanoseconds or even longer. Where the circuit frequency should be operating quicker, it actually operates slower. A majority of my paper actually focuses on delay faults as well as the stuck-at fault conditions, because they are more prevalent. Sequential ATPG testing. Sequential ATPG testing is the goal of component testing. Sequential ATPG testing provides faster testing. It allows for more testing to be completed in a given time span. It is also continuously evolving to provide shorter times between testing. The downsides are, however, the faster the time for testing, accuracy is lost over longer periods of time. This really means that while performance is increased over the shorter time frame, the propagation of losses can become greater over the n times amount of components being tested. When it comes to sequential testing, there's also can be the components of excess switching, which can lead to premature failure of not only the chip in question, but overheating the socket in question in a post-manufacturing process. There are certain types of testing used for post-manufacturing testing where this can be an issue, and that can also be remedied, which is talked about in my paper, with lower power consumption and lower switching testing with using sequential and broadside loading testing. Another downside is the high power consumption with testing because of the switching, and also high CPU usage of the computer, which can lead to more lengthier of times, and also heat production as well, not just in the CPU, but when it comes to power consumption, you also generate heat in the die and socket of the material you're testing, and this heat also leads to potential thermal breakdown. So similar to broadside loading, parallel fault simulations are used typically for and OR type logic gates, which can be tested in unison. They're tested in unison using two different logic words at the same time. Parallel testing allows for two or more tests to be run simultaneously. The speed is very high for this type of testing. The downsides of this are that serial testing is faster at determining faults, as the test will stop at the first fault, which is preferred. But with parallel faults, although you're testing more components at the same time, the runtime for the single run has to go through every single possible fault condition before it returns a fault. Deductive fault simulations. In Boolean model gates, deductive fault simulations are used. Similar to parallel fault models, with the difference being only fault-free values are used. So in this case, half the time is used, because not only it uses fault-free values, whereas in parallel or broadside loading it uses fault-free values and the test vectors which would contain a fault as well. This results in a very high speed for testing, and that single faults are determined very, very quickly. And the last topic, at-speed delay testing. At-speed delay testing is used for very high-speed applications when it comes to delay testing of models. It has delays over slow to fast testing, but it does require shorter testing times because the test vectors are being applied at the same clock rate. Another upside is that it can find faults not normally found during slow to fast testing, but the downside is loss of validation in testing can occur because of the speed of the test itself, which is also indicative of parallel and sequential testing. When you have more performance and more speed, you have a greater loss of accuracy. So what computer science engineers try to come up with is the right ratio of speed to performance, speed, performance, and accuracy of the testing. These are my references used in my paper and also my presentation. I hope this presentation was educational and informative. Thank you very much.